In this video, we are going to study the resonance in series RLC circuit in detail. And based on this, we will discuss about resonance frequency, bandwidth, quality factor, etc. Okay. And before going to this portion, already we discussed about special three cases for a series RLC circuit in the previous video. What are they? First case, if XL or the inductive reactance is higher than capacitive reactance, then the circuit will be inductive in nature. We studied that. And if capacitive reactance is higher than that of inductive reactance, that is Xc is greater than XL, then the circuit will be inductive. And the third case was when XL equal to Xc, then what will be there? Only resistance. The net reactance, inductive reactance and capacitive reactance will be absent there, or which will be nullified there. And that is the condition for resonance. Okay. When XL equal to Xc, then resonance will occur in that circuit. Okay. Here you can see three waveforms. Okay, the first figure A, which will represent the relationship between the reactants, that is XL, with the frequency F. Okay, the frequency and the reactants are directly proportional with each other, so that the variation of frequency with the reactants will be linear and will be like this. If frequency increases, reactants will be in phase with the frequency. Okay, and the figure B, you can see the relationship between reactants and frequency in capacitance. Here the capacitive reactants and the frequency, which are inversely proportional with each other. If the reactance is very higher, then frequency will be very less. Okay, so the graph is like this. We can see here at resonance frequency, you can see in figure C, at resonance conditions, these two parameters will be equal. And here you can see this graph shows the relation with the relation of inductive reactants with the frequency, and this graph will represent the relation between inductive reactants and frequency. Okay, at this point you can see, at this point this XL and XC become equal. Okay, this will be the line which shows XL and this can be XC, and at this point these two terms collides, so that is the point of resonance. That is the condition for resonance. Okay, and before this point of resonance, before discussing about that point, one term is very important, that is frequency. At the point of resonance, the frequency is a resonance frequency. Resonance frequency is nothing but it is the frequency at which the resonance condition occurs. Okay, so before this resonance frequency, the effect of capacitor is higher than the inductor. Okay, here the inductor will starts from 0 to and increases, but the capacitive reactance will starts from maximum value. So we can say that the effect of capacitive reactance is higher than that of inductive reactance, because inductive reactance which will starts from 0, and the capacitive reactance which will starts from the maximum value. Okay, so Xc is greater than Xl just before the resonance frequency. Okay, and we can see that at this time or frequency just before the resonance frequency, the circuit will act as a pure capacitive circuit. Okay, and after this point XL will become equal to XC, and after the point of resonance frequency, the effect of inductor, okay, inductor reactance is increasing from 0 to here, and this at this point it will equal to the capacitor reactance, and it is increasing going on this point which is increasing, you can see here. And after the point of this resonance, we can see that this graph shows capacitive reactance and which is decreasing, gradually decreasing or slightly decreasing, but inductive reactance is increasing after the point of resonance frequency. So that we can see that after the resonance frequency, circuit shows a pure inductive effect. Okay, is it clear? Before the point of resonance frequency, the circuit will be capacitive in nature, and after the point of resonance frequency, the circuit will be pure capacitive in nature. And this point is very important for technical exams, so we can remember this point. Okay, and based on this we can derive an equation for this resonance frequency, that is Fr. Okay, a resonance frequency Fr. We know that at resonance condition XL is equal to Xc, and XL is nothing but 2 pi Fl, and which is equal to 1 by 2 pi Fc. Okay, this frequency will be resonant frequency. Okay, so we can write this resonant frequency in the left side, other terms can be go to the right side. So Fr square will be equal to 1 by this 2 pi into 2 pi, that is 4 pi square LC. Okay, 4 pi square LC, 2 pi into 2 pi, 4 pi square LC. Okay, and from here we will get, taking the roots, we will get Fr resonant frequency. Fr will be equal to 1 by 2 pi root of LC, and this will be the equation for resonant frequency. Okay, and its unit will be hertz. And based on these terms we can write some important points at a resonance condition. They are: at resonance, what are the conditions? Net reactance will be 0. Is it clear? Net reactance is 0. Why? Because XL equal to XC, or otherwise XL minus XC will be 0. So that we can say that the net reactance will be 0 at a resonance condition. And the second important point is that the impedance will be minimum. Impedance will be minimum. We know that in an RLC series circuit, impedance Z will be R square plus XL minus XC the square. And at this case, the case of resonance, this term will be 0. So we can say that Z is equal to R only. Okay. So the impedance will be minimum at the resonance condition, so that what will be the third point? Current will be maximum, or the circuit will supply maximum current. Current will be maximum at this condition. And based on this, one more point we can write, that is the phase angle will be what? 0, because at resonance condition the circuit will be pure resistive. Only R will be there. In a pure resistive circuit, current and voltage which are in phase with each other, so phase angle will be 0. And based on this we can write the next point. If the phase angle is 0, then the power factor will be cos 0. What is cos 0? It is nothing but 1. That is, power factor will be maximum at resonant condition. Okay. And the sixth point, that can be the power dissipation. About the power dissipation. Sorry for the interruption. So this power dissipation at the resonant condition will be also maximum, that is V square by R. Okay, or I square R. Power dissipation will be maximum. So we can say that at the resonance condition, it is the condition for maximum power transfer. Okay, at this condition the circuit will supply maximum power to the load. Okay, it will transfer maximum power from the source to load. We can remember this point also for important for technical exams. Okay, and based on this concept we can discuss an important term, that is bandwidth. Here you can see a graph that shows a bandwidth. Okay, what is bandwidth? Bandwidth is nothing but it is a range of frequency. Okay, bandwidth means it is the range of frequency at which the circuit can accept or receive the signals. Okay, that range of frequency can be represented here as FL and FH. This FL means lower cutoff frequency, and FH will be upper cutoff frequency or higher cutoff frequency, which is represented as FH here. This H shows higher value. Okay, and between these points or between this frequency, between this lower cutoff and upper cutoff frequencies, the circuit can receive or accept the signals. Okay, and that range of frequency is called bandwidth. But what condition is there? At this range, the current must be 0.707 im. Okay, so simply we can say that the range which varies from lower cutoff frequency to upper cutoff frequency. So the difference between this lower cutoff frequency and upper cutoff frequency, when the current is 0.707 im, that is called the bandwidth of that particular circuit. Okay, and based on this, okay, FL is the lower cutoff frequency, and that is nothing but the difference between the resonant frequency and half of bandwidth. Okay, half of bandwidth. And upper cutoff frequency FH is nothing but the difference, sorry, the sum of this resonant frequency with half of bandwidth. Okay, we can remember this points also for solving problems. It is very important. Okay, and based on this upper cutoff frequency and lower cutoff frequency, we can write that bandwidth will be equal to difference between FL and FH, or otherwise we can say that it is equal to root of FL and FH, or we can written as some more equation will be there for find out this bandwidth, that is R divided by 2 pi L. Okay, these three equations can remember for solving problems in exams. Okay, based on this, one important point will be there, the last topic in this video, that is nothing but quality factor. Okay, quality factor is closely related with the voltage. Okay, it is represented by Q0 or QC. Okay, and it is closely related with voltage magnification. What is voltage magnification? Voltage magnification is nothing but it is the ratio of voltage across inductor or capacitor upon the supply voltage. Okay, voltage across the inductor can be VL or VC divided by the applied voltage, that is V, but the voltage will appear across a resistor only at resonance condition. Okay, the effect of reactance of inductor and capacitor will be 0, but the voltage drop will exist only across the resistor. So that we can say that we can write here as R, and the above point we can choose the inductive effect. Okay, omega R L by omega R into L divided by capital R. What is this omega R? Omega R is nothing but 2 pi F, that is omega R. Okay, 2 pi FR by FR into L by capital R. Okay, we know that at a resonant frequency FR is equal to 1 by 2 pi root of LC, and from here we can replace this 2 pi and FR from this equation. Okay, 2 pi and FR can be rewrite as 2 pi into Fr will be equal to 1 by root LC. Okay. So in this equation, we can replace this 2 pi Fr by this 1 by root of LC, and finally we will get the quality factor QC or Q0 will be equal to 1 by R into root of L by C. Okay, this equation is very important for solving problems. Okay, these are the major points about the resonance in RLC series circuit. Okay, thank you.